Welcome to the 10-minute KQL channel's Kusto Query Language Advanced Series full course. These are all the topics previously covered in the Beginner and Intermediate series. The Advanced series layers on these additional skills to help you become more functional in the language. This full course gives a short explanation and at least one example per concept. If you want more in-depth instruction with additional use case examples, review the Advanced Series playlist on the 10-minute KQL channel for 10-minute long videos with homework challenges to get hands-on practice for each topic covered. In the future, we'll make a Security Analyst playlist to help new analysts with best practices and tips. If there are any additional subjects you're interested in learning, please let us know in the comments. In this full course, we'll be using free data sets in Azure Data Explorer, or ADX for short, found at kc7cyber.com. This is a free cybersecurity-focused site that uses datasets simulating compromised companies so you can practice your KQL investigation skills in a practical scenario. The first general topic we want to cover in the Advanced series is how to manipulate dynamic objects. If you remember the first lesson in the Intermediate series, we talked about the KQL data types, how to cast to different data types, and how to verify the data type in the schema. Fields that are set as a string data type can easily be changed to dynamic using either todynamic or parse JSON. While it's more common to see parse JSON, we wanted to mention todynamic because you may see it in some queries. Personally, I prefer todynamic because it follows the same logical format for casting, just like toString or toInt. Remember, when you cast to a dynamic data type, you lose some level of functionality. You may find you trigger an error when trying to use distinct or summarizations. And in these cases, the field should be cast back to a string or other data type before performing these actions. In this example, I have 5 fields projected. I see the status and device detail fields are JSON objects, full of key value pairs in curly braces. When we look at the schema, we can confirm those 2 fields are a dynamic data type. We want to use summarize so we can get a count of each combination of the fields. When we try to summarize, we get an error because of the dynamic data type. When we cast both data types to string, then the summarization works. Remember that JSONs are key value pairs that are in curly braces with objects separated by commas. Many times these JSON objects are stored in the database as a dynamic data type, just like our previous example. But you can also find them stored as a string data type. While it's possible to parse the data we want with either a string or dynamic data type, it's easier to do it with dynamic. When we examine the JSON within the status field, we see it has 2 keys. The first is the error code, and the second is the failure reason. We also see that sometimes there's only 1 key, and other times there are more than 2 keys, including an additional details key. If we're only interested in extracting the error code key from the JSON and placing it into his own field, we can. Or if we want, we can take all the keys and make them into their own fields. The first parsing technique we'll teach is the easiest, but it uses the most amount of resources, and it's the least efficient. If you want to make all the keys inside a dynamic JSON object into their own individual fields, you can use evaluate bag unpack. In this case, you can think of the dynamic JSON as a bag, and we want to unpack each item from the bag into its own column. If you try to use bag unpack on a string, it will fail. So be sure to cast the JSON object to a dynamic data type if needed before using bag unpack. Also, each item placed in the bag can have its own unique data type. Just because the JSON object is cast to a dynamic doesn't mean all the objects inside retain the dynamic data type when taken out of the property bag. So let's go back to our original 5 fields, where we know 2 of the fields are dynamic JSON objects. Let's type in evaluate bag unpack. Then we'll place the name of the field we want to parse out in the parentheses. When we execute the query, we see the original 4 fields on the left haven't changed, but as we scroll right, we see all the keys that were inside the JSON associated with a status field are now parsed into their own individual fields. We should also take note that the original status field is no longer present. Once the information is parsed, it can then be queried. In this example, we want to only see records where the parsed out error code field is not 0. Before we parsed the keys in the status field, the field was a dynamic data type. If you look at the schema after using bag_unpack, we can see the device detail field with our second JSON is still in dynamic. But the 3 newly created fields that represent the keys that used to be in the status field are in a string or long data type after taking them out of the bag. Now let's use bag_unpack on the device detail field to parse the JSON. When we scroll to the right, we see that all the keys from both dynamic JSONs are now in their own fields. When we look at the schema, we also see the data types of the keys inside both JSONs have still retained their original values once unpacked. One thing to watch out for is duplication of field names. If the table already includes an exact match of the key name you're trying to unpack, it will produce an error. In this example below, we have the same 5 fields we did before, but instead of the user agent field, we change the name to error code, because it's one of the key names inside the dynamic JSON object in the status field. If we try to use bag_unpacked on the status field, we get an error now, because it can't produce a second field with the exact same name, unless we tell it how to handle that error. If you receive an error like this, it can be resolved by adding a prefix to all the parsed out fields. We can add a comma after the status field name, add quotes, and then add something easy like an underscore character. When we execute the query, we no longer see an error, and all the newly parsed out fields associated with a status JSON all have an underscore prefix. You aren't limited to an underscore prefix. It may add value if you name the prefix as the original field name to help you remember where each field came from. This can be especially useful when you have more than one JSON object to parse. Since the objects inside the property bag retain their data type when taken out of the bag, we may have a use case where we want to cast a new data type as we're taking them out of the bag. In this example, we have the device detail field that has a dynamic JSON. If we wanted to change 3 keys to a dynamic data type as they were taken out of the property bag, we could do it like this. When we look at the schema, we can now see that all 3 fields are cast to dynamic data types. Sometimes you have a JSON object which has key value pairs and curly braces, and it's stored as a string data type. To leverage many of the useful parsing functions in KQL, the first step is to cast the JSON to a dynamic data type. We can do this by either using parse JSON or todynamic. Both serve the same general function in preparing the objects for parsing or manipulating as a dynamic data type. In this example, we have 2 fields that contain JSON objects. As we look at the schema, we see that the status field is set as a dynamic data type, and the device details field is set as a string data type. In this example, we want to take a single key from inside the status JSON and make it into its own field. Remember, if we want to create a new field in the table that doesn't already exist, we can use extend. In this case, let's extend the error code key and make it its own field. This will create a new field called error. When we define what the new field will contain, we can reference the status field first, use a period, then reference the key inside of the JSON that we want to parse into the new field. When we execute this query, we see that the newly created error field contains the error code. We see the status field containing the original dynamic JSON is still present. And when we look inside of the JSON objects in each record, we can see the error code key value pairs match the new error code field. When we examine the schema, we see that the original status and device detail fields haven't changed, and the newly created error field is set to a dynamic data type. Remember, in the last session, when we used evaluate bag_unpack, the items kept their original data types when taken out of the bag. But using this method of casting from a string to a dynamic data type, the data type of each key value pairs becomes dynamic. If we wanted to summarize or use distinct, we would have to cast to a different data type. In this example, if we want to cast to an integer, we could do it like this. If you remember, the device detail field is in a string data type. Let's see what happens when we try to pick a key to extend. Let's choose the first key of device ID. We get an error. It fails because the JSON object is in a string data type, and it must be set to a dynamic type to use this type of parsing syntax. In this case, we can use parse JSON or todynamic to cast to a dynamic data type. We'll create a new field called dynamic device detail. When we run the query, we can see it duplicates the device detail field. But when we check the schema, we can see that the parse JSON function simply changed the data type of the same JSON object from string to dynamic, unlocking the dynamic syntax for us to use. If we go back, we can also use todynamic to do the same thing. Parse JSON and todynamic are synonymous in the same way that sort by and order by are synonymous. Now that we have the device detail field in a dynamic data type, we can easily take one of the keys and make it into its own field. We can see that most of the fields are empty, and only a few have PII removed as values. If we wanted to now parse the second key of operating system, we can use the same method. When we run the query, we can see the operating system field is parsed. In the last examples, we used extend to create a new field. Let's go back to our original two JSON objects and use an alternate approach using project. Remember, the status field is already set to a dynamic data type. In this example, we want to project our two main JSON objects, plus we want to project the error code key as a new field. This worked in the same way that extend created a new field, except we accomplished the same thing using project alone. You can see that by casting to a dynamic data type in KQL, you can easily parse and manipulate JSON objects using either bag unpack, extend, or project, depending on your preference or your use case. We also see that when we extend or project, we may need to cast the newly created fields to a data type that we can better manipulate later in the query, as we cast back to something other than dynamic, such as a string or integer. We also want to show some use cases where you may receive an error trying to parse a JSON. In this example, we've projected the status field and authentication details field from the sign-in logs table. When we look at the schema, we see the status field that was used in our previous examples is dynamic, and the authentication details field is a string. Using the previous steps, we can try to cast the authentication details field to a dynamic data type using parse JSON. Then try evaluate bag unpack. When we do this, we see that it doesn't unpack any keys into their own fields. When we look closer at each record, we see the curly braces and the key value pairs associated with a JSON. But we also see brackets encasing the JSON in the authentication details field, but not in the status field. These brackets provide an additional challenge to navigate when parsing. The brackets identify an array, which is a collection of elements stored together. In previous lessons, we used pack array when creating variables with multiple values. In those use cases, we made our own array. Now we need to find a way to remove objects from the array or otherwise manipulate the array so that we can parse the items inside of it. In this case, the JSON object, full of key value pairs, surrounded by curly braces, is the object inside of the array. It's also possible to have multiple JSON objects inside of a single array. Before we discuss how to parse these, we want to cover the topic of indexing. In this simple example, we have an array with 3 elements in it. In KQL, the first element in the array is considered at index position 0. In this case, it's the string test. The number 52 is considered at index 1, and the last element of desktop 1, 2, 3, 4 is at index position 2. When we represent these index values in the query, we use brackets. If we wanted to reference the second element of the array, we can use the number 1 surrounded by brackets, which in this example represents the number 52. When we look at the schema, we see the authentication details field is a string data type. First, let's cast it to a dynamic, so we can try to manipulate it more easily. When we look at the schema, we verify that both fields are now dynamic. Let's try our normal extension method and see what happens. It does make a new field called test, but there's no visible values in the field, so this didn't work for us. Let's take a closer look at this array. When we expand one of our records, we see our two fields, and when we expand our authentication details field that we're trying to parse, we see a 0 and a 1. These represent the elements inside of the array. The first is at position 0, and the second is at position 1. There are two separate JSON objects in this array. Before we can parse it, we need to identify which element within the array we want to parse. We can do this by adding the element index at the end of the field name. Here we add a 0 in brackets to represent the first JSON in the array. Remember, the first object in an array is indexed at position 0, and the second object is positioned at index 1. When we execute this query, we can see it successfully parsed the key that we're referencing. We learned that even if we have a JSON inside of an array, we can still make sure that the field is dynamic. Then we can identify the element in the array we want to parse from, and lastly, identify the key we want to parse. Now let's show an alternative method to work with arrays. We know that the authentication details field has an array with two elements, both of which are JSON objects. We can take each element out of the array and make it into its own record by using mvexpand. Before we show mvexpand, we want to refresh on a concept in the intermediate session. We use summarize along with makeSet to take values from multiple records and compress them into a set which is displayed horizontally in one record. In essence, with the array problem set, we can use mvexpand to do the reverse. We can take items that are compressed horizontally into one record, and we can make them into their own individual records stacked vertically. The MV in mvexpand stands for multi-value, and in this case, we have two JSON objects or values that we want to expand vertically. To use mvexpand, the fields need to be in a dynamic data type. Next, let's use mvexpand and place the name of the field we want to expand in parentheses. When we execute this query, we now see that the brackets that used to encase the two JSON objects are now gone, and each JSON is in its own record without brackets. If you look closely, there are duplicated time fields for every two records, because those time fields were present in both JSON objects. Now we can select a key inside of the JSON to parse using extend. We'll make a new field called auth method that will show the authentication method detail key. When we execute this query, we see that the value is in every other record, because that particular key was only in the first JSON object and not in the second JSON of each array. When using mvexpand, you may find that some arrays may have 10 or more objects that are extracted. When this happens, any fields in the record that are constants will be duplicated, and any variables associated with the expansion process will be new in each record. Depending on the use case, you may need to summarize the data after using MV-expand. Now that we have several ways to parse JSONs that are part of an array, let's talk about nested JSONs. In the last example, we had an array that contained two separate JSON objects. It's possible to have a JSON object that has a JSON inside of the JSON. This is called a nested JSON. To better understand the concept, we created our own test data set. When we take a look at this output example, we see a single JSON that has the first key value pair, which looks like what we're used to seeing, and a second key which has a nested JSON. Inside the nested JSON are additional key value pairs. While this example has one layer of nesting, it's possible to have multiple layers of nesting. We casted this field to a dynamic data type, so it's already ready for parsing. First, let's extend key 1 like we normally would. We can see that it works. So now let's try to extract values from nested keys. We can see the parse worked. We simply added a second period, which identifies the nested key to parse. If we wanted to extend the second nested key, we could use the same method. Let's move on to parsing strings. First, let's have a look at the email logs by taking a sample. This shows basic information on email activity in the company. In the far right column, titled Link, has the URL to embedded links within each email. For our first example, let's isolate that field so we can practice parsing it by using distinct. As we look at the schema, we can see that it's in a string data type, which is perfect for our parsing functions. If we want to parse out only the domain from each link, we can use parse URL. We can create a new field using extend, title it with the appropriate name, then define what's in the new field using parse URL. We place the name of the field we want to parse within the parentheses. When we execute this query, we see that a JSON is created, which has taken the URL from the link and parsed it into standardized key value pairs. If we examine the keys, we see the first one, titled Scheme, displays whether it's in HTTP or HTTPS. We can see the second key of host has the domain. We can see that some but not all URLs have a path leading to a file name. For those, the path is parsed out. If we wanted to parse out the domain only from each URL, we could select the host key. It's much like using parse JSON, where we can place a period, then the name of the key we want to parse. When we rerun this query with a key defined, we see the domain field has the parsed domains from each link. When we examine the schema, we see that the parse URL changed the data type to dynamic in the same way that parse JSON did. If we needed to summarize this data and we need to take it back to a string data type, we can incorporate that in the same record like this. Everything in the parentheses will be run as dynamic. Then the toString function will be applied. As we rerun the query, we can see that the data type is now changed back to a string. Keep in mind that as your data sets grow, some parsing functions can take a long time to finish, and some may fail to complete the function at all, depending on the size of the data set. So it's best to filter the output first so you're only performing the parsing function on the records that you need. Let's move on and sample a new table called File Creation Events. Let's narrow down our filter to distinct paths where files were created on host devices. For this example, we'll just take a sample of 100 records. If we want to parse out different values from this field, we can use parse path. When we place the name of the field we want to parse in the parentheses and run the query, we can see it also creates a JSON with key value pairs in set patterns, just like parse URL. We can then select different keys we're interested in. Let's parse out the root path, directory path, file name, and extension. We can see each section is now easily parsed out, and we can filter on these fields more easily. When we look at the schema, we can see that all the parsed out fields are set to dynamic. If we wanted to parse out all the fields, we could also choose to use evaluate bag unpack like this. The advantage here is that all the fields are automatically in a string data type, so there's no need to transition back from dynamic if you need to use distinct or to perform summarizations. Another common piece of information that's useful in a digital investigation is the user agent. Let's go to the outbound network traffic table and take a sample. We can see which IP sent the traffic, whether it was a GET or POST method, the URL that was navigated to, and the user agent that facilitated the traffic. There are multiple elements embedded in each user agent, and we can parse those elements out of the string using the parse user agent function. We have three parsing options to choose from. One is the browser information, one is the operating system information, and the last one is the device information. If we start out with the browser, we can see it parses out all the relevant browser information. You can also see that there's a nested JSON, so if we need to parse out specific keys, such as the family, we can refer back to our parsing nested JSON lesson, and we can parse it in this way. If we want to parse out the operating system from the user agent, we could change it from browser to OS. If we wanted to parse out the operating system type, we could do it like this. Lastly, if we wanted to parse out the device information, we could change OS to device. But this may not be available in all user agent types depending on the data set you're working with. Sometimes we have a string and we want to add something to each record in the field. When we need to add characters to an existing string, we can use strcat. This is short for string concatenation. First, let's look at the employees table, and we'll isolate the username and company domain fields. If we wanted to create a new field that joins the two fields together, we can use the string concatenation function. First, we extend a new field and give it an appropriate title. We use the strcat function, and in this scenario, we can place the name of the field first, a comma, then the name of the second field. When we run this query, we can see that the strings in the two fields are now joined. If we wanted to add an @ symbol between the two strings, we can add it in with quotes like this. When we rerun the query, we can see it added an @ symbol between the two strings. Now that we know how to add things to strings, let's see how we can take things away from strings. Let's go back to our original two columns. In this example, we want to take away the .med at the end of the company domain. We can use the trim function to take characters out of a string. There are 3 variations of trim. The regular trim function removes all the characters that you define from either the front or the back of the string. Trim_start only removes the characters you specify from the beginning of the string, and trim_end removes the characters from the end of the string only. In our example, if we want to remove the .med, which is at the end of each string, we can use trim_end. We need 2 arguments in the parentheses. When we look at IntelliSense, it helps us remember what the 2 arguments are. The first argument defines what we want to take away. In this case, we want to take away .med, and it's in a string, so we put it in quotes. We place a comma, then define the second argument, which is where we want to take it away from. In this case, we want to apply it to all items in the company domain field. When we execute this query, we can see it gave the expected output. When you have a character or group of characters in a string that you want to identify and substitute, we can use replace. When we look at the employees table, we can see a field for email addresses in the fictitious company of Castle and Sand. Let's focus on that field and replace all of the instances of .com with .net by using the replace function. When we extend a new field and type in replace, we have several options. Since this field is a string data type, for now let's type in replace_string. The parentheses have 3 arguments. The first is where you want to perform the replace function, and in this case, it's in the email address field. Next, we place what we want to be replaced, and lastly, what we want to replace it with. When we execute this query, we can see the changes were made rapidly on 1,500 records. In our next example, we're looking at the file creation events table and projecting only unique host names. We see a normal pattern of some numbers and letters, followed by a hyphen, followed by the machine type. In this example, we want to divide the field. Our goal is that we only have the machine type in one field. We can use the split function for this task. We can extend a new column and type in the split function. Our arguments will be where we want to perform the split and what we want to split on. In this case, we can split on the hyphen. We can see the output is in the form of an array, in which there are 2 string objects. Do you remember how to parse an array? In this case, we can use parse JSON and reference the index value of 1 to represent the second object in the array. If we wanted to summarize or use distinct on the output, we'd get an error because the data type is currently dynamic. So if we wanted to perform those actions, we can change the output back to a string like this. When we rerun the query, we can see the machine type field is reset to a string, and we can perform a summarization on the field without error. There may be times when we need to make the letters in a field either all uppercase or all lowercase. In this situation, we can use either 2 upper or 2 lower. As we extend a new field, we simply type in 2 lower and place the name of the field of interest, and it performs the expected output. When we change the function to 2 upper, we can see the output is now in uppercase. In the beginner series, we talked about using double equals, has, and contains to find and filter for items of interest. Each has a different level of precision and requires different levels of resources to execute. These take care of most of our searching and filtering needs. If we need more options beyond a basic string search, we can use REGEX. REGEX is short for regular expression and can be used to find or find and replace patterns in a string. There are many forms of REGEX, and KQL supports the RE2 form. You can conceptualize regex as its own language, and RE2 as a dialect of that language with unique syntax. As an example, let's go back to the process events table and look at distinct host names. We could easily search for exact matches using double equals. We could match on the machine type after the hyphen because it's a delimiter using has, or we can match on substrings using contains. What if we need to find host names with no numbers in them? In this case, we could use matches regex to assist us. We can use where to filter, then use matches regex with a space between the two words. In the quotes, we can place our regex statement. When we run this query, we can see it's filtered for host names without any numbers in them. Regex is a powerful tool for finding patterns using matches regex, but it can take considerable resources in some use cases. The initial caret symbol indicates the beginning of the line, and the dollar symbol indicates the end of the line. Next, we have brackets, which mean a character class. In this case, the 0 to 9 references numbers. The caret before the numbers is a negative, so think of it like an exclamation point in KQL. Up to this point, we're just saying no numbers. The asterisk means that the pattern we identify can appear in any number of characters in the field. There are also many different ways to write a regex-based statement and get the same results, since the language also has shortcut symbols. Let's move on to Base64 decoding. We can see that one unique PowerShell Base64 encoded string is found in the environment. In this case, we want to extract the actual Base64 string into its own field. We can first extend a new field and use the extract function. Since we're using regex here, we need to place the first dash and include all possible encoding aliases in PowerShell to find, then extract everything after the encoding. After the comma, we see the number 2. This represents the capture group we're interested in extracting. In this case, the first capture group would be one of the encoding aliases, and the second capture group would be everything after that. So we select 2 for the second group. Lastly, we identify the field to execute this in. When we run this query, we can see the extracted Base64 is now in its own field. But there's one problem. There's a quote at the end, which is not part of the Base64. So let's remove that with a trim end function. Now that it's cleaned up, we have the Base64 string isolated. If we wanted to decode the Base64 string to identify what is being executed, KQL has a Base64 decode toString function to help us out. When we run this final query, we can see the decoded string and better understand what is being executed. In this case, the command uses PowerShell to call a WMI method to install software updates on a machine. While this is likely benign in nature, it may be something to look further into. Let's transition to working with IP addresses in KQL. We can use the IPv4 isPrivate function. This gives us a true-false value whether or not the IP is internal. As we extend a new field and use the new function, we simply place the field we want to conduct the true-false evaluation in the parentheses, which in this case is the src_IP field. When we run this query, we can see that some are true and some are false. If we want to identify a range of IPs, then identify if the IPs in our dataset are in that range, we can use the IPv4 is in range function. We can define which field to analyze, then define the range, and we receive a true-false value. If we need the subnet mask to be parsed out and identified, you can use the IPv4 netmask suffix function. If no subnet mask is present in the field, the default will be a mask of 32. If we have a list of IPs and we want to associate a geolocation with each IP, we can use the geoinfo from IP addresses function. Keep in mind that the geolocations associated with IP addresses are not precise and should not be trusted as an authoritative source of location. You can see that internal IP addresses do not present a location value, but public IPs do in a JSON format with a country, state, city, and lat-long keys with associated values when they're known. When we check the schema, we can see that the JSON is already in a dynamic data type, so it's ready to be parsed. We can easily use evaluate bag unpack to parse the keys into their own fields for filtering. We can also summarize a count by country. When we look at IP addresses, they're in dotted decimal notation, and they consist of 4 octets separated by periods. If you need to convert to a big endian version of the IP to be used in calculations or for comparisons, KQL has a function for this. This conversion takes all the binary values of each of the 4 octets and it concatenates them all together, making one long binary string of all 4 octets. Each octet is multiplied by a specific exponent to create a final value. If the big endian number is needed, we can use parse IPv4. You may have a starting IP and an ending IP associated with a range of IPs and want to find all the potential CIDR ranges possible. In this case, we can use the IPv4 range2 CIDR list function. In this case, we're just creating a new field with a start and end IP for our range. When we run this query, we see the potential subnets in that range. This could be useful for network admins that need to configure subnets within a given range. In addition to the IPv4 functions shown in this session, KQL also has functions for IPv6. We can transition to Evaluate Pivot next. As we take a sample of sign-in logs, we can see many different fields of interest. but scrolling through them all left to right doesn't present well. As we narrow it down to a single record of interest using argmax, our goal is to capture this information in the best way for case notes. Using evaluate with the narrow function places each column as its own record in a key value pair format. This may be what we need already, but we can make this data even more presentable by removing the initial field full of zeros and adding a colon after the column values. Sometimes when we write complex KQL queries, we need to call on the same data set multiple times. If a data set logs a high volume of records, there may be additional records added from the first pool to the second pool, which can lead to data errors. Pulling the same data set twice when not needed also requires additional resources and increases the likelihood of the query timing out, depending on the size of the data and the system used to query the data. Instead of calling the same data set multiple times, we can pull the data once and save it in a temporary state, then call the same saved data set again later in the query. In this case, we can use the Materialize function to save our data set that we plan to reuse. We can create a variable for our saved subquery in this general format. The subquery portion represents any query that you'd like to save as a temporary output table. In this use case, let's first create a query that we'll use as our snapshot. In this example, we want to take a snapshot of all sign-ins in the last week. We made changes in our environment several weeks ago, and we want to look for applications and resources no longer having authentication attempts or success. If we had to call this data more than once, it's possible new sign-in records could have been logged, skewing the results. When we run our subquery, we see it gives us a snapshot of sign-in activity in the last week. We can now place this query we want to use in our Materialize function. There are many stylistic choices here to make the code more readable. One option you may see is having the initial function parentheses on one line, indenting the subquery, and placing the closing parentheses and semicolon on the far left, so it can be more easily identified as the end of the subquery. This is personal preference, however, and it's not required for the subquery to work properly. Placing the closing parentheses and the semicolon on the same line is also common. We can now write the rest of the query and refer back to the saved snapshot as needed multiple times without additional records being written. In this case, we can create 3 variables, one for result type, one for app display name, and one for resource display name. We can then extend some new fields that provide a true-false value, whether or not the apps, resources, or error codes are in our data snapshot. If the value is true, then the apps or resources were seen in the baseline period, but were not seen in the last week. Or we could easily reverse this query and identify new apps and resources that are being used in the last week that were not used in the baseline period. When we use Materialize, keep in mind that there's a maximum cache of 5 gigabytes of data. So if you're working with large data sets, you may need to rewrite your query using different strategies like distinct or argmax. If we were working with a large data set, in this use case, we could further optimize the query by taking out the time-generated field and changing project to distinct to narrow down the initial snapshot results to only unique values. Another good use case for Materialize is unioning two tables together. You might want to take a snapshot of a table, then run multiple different calculations on the same data to see the different outputs, then union the data back together. Materialize is great for these types of use cases, but keep in mind that using Materialize when it's not needed may actually use more resources than not using it at all. When we string together multiple sets of instructions inside of a query, we can save it as a variable. That variable can be called for the life of a query. But if we need to use the same sequence in a different query, we need to redefine the variable. Functions can be a way to save and later call the same set of instructions in any query we want. Let's try a sample use case. We want to create a function that will provide the square of a number. We want to call the function square. We want to be able to use this new function in any query moving forward without having to rewrite it. And we want to be able to change the logic of a function in a single place and have it propagate to other queries. In order to create functions, you need to have the ability to write, or you'll get an error. When we write this function and execute it, we can see each component is listed in unique fields within a record. When we expand the database and expand functions, we can see the newly created math functions folder that we defined earlier. Inside of the folder, we see our newly created square function with an fx before it. We also cast the input value of the square function to a real data type. Let's test out this new function and see how it works. We can use print result, then place an equals, then use the function with a number in parentheses. We can see the output is 36, which is 6 times 6. When we created the function, we cast the input to a real data type. Let's see what happens if we place a number with a decimal in the function. We can see that the output is modified. If we want to modify the function and cast it to an integer instead of a real data type, we can. If we simply change the data type to int and rerun the line, it gives an error, saying it can't be executed because it already exists. If we change the first part from .create to .create or alter, it will allow us to modify the existing function. Now let's test out the modified function with the value of 6. Then the value of 6.1. What happens if we use 6.9? And finally 7. We can see that the output rounds down to the nearest integer. We could also create KQL functions for converting Fahrenheit to Celsius, or other types of functions commonly used in our work environment. That's all for the KQL Advanced full course. If you have feedback or additional topics or use cases you'd like to see, please leave a note in the comments.